I am Jvn Dr Srivastava from the Department of Science under the Faculty of Education and Methodology, Jyoti Vidyapeeth Women's University, Jaipur. Today we will see rank and nullity theorem. Let U and V are vector spaces over the field F and let T be a linear transformation from U to V. Suppose that U is the finite dimension, then rank of T plus nullity of T is equal to dimension of U. Let n be the null space of T, then n is a subspace of U since U is finite dimension vector. Therefore, n is also the finite dimension. Let dimension n is equal to nullity of T is equal to K. And the set alpha 1, alpha 2 and so on alpha k is the basis for n. Since the set alpha 1, alpha 2 and so on alpha n is a basis for n, then it will be the linearly independent subset of U. Therefore, we can explain it to form a basis of V. Now, let dimension U is equal to n. And let alpha 1, alpha 2 and so on alpha k plus 1 and so on alpha n is a basis of V. Then the vector T alpha 1, T alpha 2 and so on T alpha n are in the range of T. We claim that the set T of alpha k plus 1, T of alpha k plus 2 and so on T alpha n is the basis for the range space of T. First, we shall prove that the vector T alpha k plus 1, alpha k plus 2 and so on T alpha n are linearly independent. Let Ck plus 1, Ck plus 2 and so on Cn belongs to F such that Ck plus 1 T of alpha k plus 1 plus Ck of 2 plus k plus 2 T alpha k plus 2 and so on Cn T alpha n is equal to 0. Then T Ck plus 1 T alpha k plus 1 plus Ck plus 2 alpha k plus 2 and so on Cn alpha n is equal to 0. Since T is linearly independent, it means these vectors belong to N2. That implies C1 alpha 1 plus C2 alpha 2 and so on Ck alpha k minus Ck plus 1 alpha k plus 1 minus Ck plus 2 alpha k plus 2 is equal to 0. Since alpha 1, alpha 2 and so on alpha n is the basis of U, that implies C1, C2 and so on Ck plus 1 and so on Cn is equal to 0. Therefore, Ck plus 1 T alpha k plus 1 plus Ck plus 2 T alpha k plus 2 and so on Cn T alpha n is equal to 0. If and only if Ck plus 1 is equal to Ck plus 2 and so on Cn is equal to 0. Hence, T alpha k plus 1, T alpha plus 2 and so on T alpha n are linearly independent vector of the range of T. Range of T. Now we shall show that the vector T alpha 1, alpha k plus 1, T alpha k plus 2 are the linear span of range of T. Let beta belongs to range of T, then there exists alpha belongs to U such that T of alpha is equal to beta. Since alpha belongs to U and alpha 1, alpha 2 and so on alpha n is the basis of U, that implies alpha is equal to A alpha 1 plus A2 alpha 2 and so on A n alpha n, and beta is equal to T of alpha, that implies T of A1 alpha plus A2 alpha 2 plus and so on A n alpha n. That implies A1 T of alpha 1 plus A2 T of alpha 2 plus and so on An T of alpha n. Since T is linearly in transformation, then T of alpha 1 plus T of alpha 2 and so on T of alpha k is equal to 0, since alpha 1, alpha 2 and so on alpha k belongs to Nt. That and beta is equal to alpha k plus 1 T k plus 1 plus alpha k plus 2 T alpha k plus 2 and so on An T of alpha n. Therefore, the set T of alpha k plus 1, T of alpha k plus 2 and so on T of alpha n is span of the range of U. Hence, it is the basis for the range of T. Rank of T is equal to n minus k. That implies rank of T plus nullity of T is equal to n minus k plus k is equal to n. This is the dimension of V. Now the next example. So that the mapping T is such that V3R tends to V2R defined as T A1 into A3 is equal to 3A1 minus 2A2 plus A3 comma A1 minus 3A2 minus A3, a linear transformation. Let alpha is equal to A1 into A3 and beta is equal to B1 B2 B3. We know that the linear transformation T of A alpha plus B beta is equal to A into T alpha plus B into T beta. A alpha plus B beta is equal to AA1 comma AA2 comma AA3 plus BB1 comma BB2 plus BB3 is equal to AA1 plus BB1 plus comma AA2 plus BB2 comma AA3 comma plus BB3. So T A alpha plus B is equal to AT apply करेंगे, then we open this by this T A1 comma A2 comma A3 and arrange. Then we can write A T of alpha plus E T of beta. Therefore, T is the linear transformation. Thank you.